Has anyone figured out whether this is real yet? Seems real to me, rather than a spoof. Yeah, fine. Oxygen mask off, I guess. I guess it is quite high. Everest 30,000, right? And you use oxygen to get up there. They start off at 25,000 feet by the looks of it.
There goes the oxygen mask. Now at 12,000 feet, you'll hear a beep in his helmet. That will tell him he's halfway home. Momentarily, we'll see the jump team pull their chutes, and that means Luke
Yeah, fine.
is all alone for the rest of the way. At 6,000 feet, you'll hear
Luke.
another beep in his helmet. There goes the chutes.
For everyone
Luke is
else.
on his own. And the crowd on the ground looking up, they have a visual on him right now.
That's an awful small postage stamp to me.
He's in!
Yippee!
And he's kicking and moving.
He's kicking and moving, that's good. I guess the main thing, it's kind of binary. Either you hit the net or you don't. And the outcomes are a little different based on those. Oh, yeah, maybe that's his girlfriend, happy that he made it. Or perhaps unhappy, who knows. Might have had an insurance policy. Was this on Monday's video? Did anyone look at Monday's video, by the way? Oh, you didn't take my admonition that you should come to prepared with the previous video already viewed? I think this was. And so both of these items relate to what was talked about, would have been talked about on Monday, which is frames of reference, which we'll briefly address today, but not in the same detail as on Monday. And so both of these videos that we're looking at relate to that. So the frame of reference is that the guy, Luke, falling through the sky, when you write Newton's second law for him, F equals ma, those are the forces, the out of balance forces are what are accelerating him at the speed of acceleration due to gravity. Air is rushing past him and there's drag on him, and so the terminal velocity, which is probably about 100 meters a second or 200 miles an hour, results when those balance. And then you go at constant velocity based on that force balance. But you have to use the correct frame of reference for him, which is him moving through the atmosphere. And so you have to attach the frame of reference to him. And so also kind of illustrated here is this FDNY of a tug in the Hudson River, I guess, New York Harbor, going down the river. And so it matters, the jet of water that's squirting out of this boat, if it's coming out at 1 meter a second, if you're standing behind it by the jet, then it looks like it's coming out at 1 meter a second. But if the boat is also moving at 1 meter a second, then to someone who stands on the land, then the jet is coming out at 1 meter a second and the boat is moving at 1 meter a second. So a drop of water at the front of that would be going 1 meter a second because of the boat and 1 meter a second because of the jet. And so the relative velocity is what we sometimes need to use to be able to take care of that. So we have to think about frames of reference. And so these two things demonstrate exactly that. And so that was what was Monday's online stuff. So we'll do a quick recap of what's going on. Yeah, so the best diagrams to explain it are these. And so what we'll talk about today, now that on Monday you have some command of reference frames, is we'll talk about conservation of mass. Mass in minus mass out equals accumulation. And so we'll define some control volumes. And these can be of three flavors, shown here. One is a fixed and static control volume. So it's fixed and constant volume. So if you look at flow in a pipe, you can imagine a section of that pipe, Bernoulli upstream, Bernoulli downstream, has to be steady state. So the same mass flow rate has to be going in as is coming out if you're not accumulating material on the inside. You could think about a constant volume container, but one which is physically translating. So constant volume but translating, be a jet engine, I suppose. If it's sitting on the runway, then it's static. If it's moving along the runway or in the air, then it's physically moving from one location to another. And moving and deforming would be blowing up a balloon and just releasing it. And you know exactly that two things will happen. It will be mobile because it will have a jet coming out of it, and it will also change its volume as it loses volume of air within it. And so the reason that we want to think of those three volumes is that those are the gambit of what we have. Static and not changing volume, moving and not changing volume, and moving and changing volume are the three permutations of that behavior. We talked about material derivatives last time. We'll cover that just very briefly this time. The example was of a change in temperature as you go down into the earth. When you drill well bores, you often put tools down a well to be able to look at geophysical signatures, gamma ray counts to look at for clays, temperatures if you're prospecting for geothermal reservoirs. And so if you go down in a hole, the temperature that you'll see if you're attached to that sonde would be a change in temperature with time. But you'd like to be able to convert it to a change in temperature with elevation. And so you can use the material derivative to do that. And we'll follow that today. Won't go back through that. And so for the material derivative, it merely is something that's attached to a person. This would be a mass that's attached to me as I'm falling through the sky, or Luke as it was. And we can define it into terms which are fixed reference frame. And we'll do a quick example just to reinforce that. How behavior changes in time and how behavior changes in space. And these together, if you know how it changes in time and space, such as in Bernoulli in going upstream and downstream, you can calculate how a particle of fluid going through that stream tube would behave in terms of its mass change or its velocity change would be typically what we do. So I won't go through that again, just merely note that that would be in the stuff to look at online. And just to reiterate the fact that we've kind of accommodated that here. So that's control volume. So talk very briefly about that, and we'll talk more about that today. The material derivative is pretty straightforward. We've kind of seen it. Perhaps I'll move down here and start again. It's worthwhile getting this lodged in your mind relative to things that we've already done. And so we've talked about free jets, right? And a free jet looks like this. And we have water coming out. We have a height. And we know a couple of things about a free jet. We know that it accelerates as it goes downwards. And we could write a couple of points here. And what did we do before? We called this one h. And we called this one lowercase h, I think, in the example we did. And we could write points 1 and 2 and 3. We know that on this surface, P1 is equal to 0, V1 is equal to 0, because it's a big tank. And so we know that Z1 relative to where we take our datum is given by that height. If we choose our datum at this point here, we know that the velocity at 2 from writing Bernoulli is 2g, let's do it z. Let's kind of ignore the fact that we're writing z upwards for now. And we're choosing square root, right? That's what we had. And we had also that nothing changes here in that this is also 2gz square root. And the only difference between these is that this z would be uppercase h, and this z would be uppercase h plus lowercase h, right? The total distance. Because this is h plus h, this has to be bigger than this. And so from continuity, V2A2 equals V3A3. So we know that A3 has to be smaller, so it must neck in. We said that. And we could think of this also as being Luke. Well, that's pretty good, actually, isn't it? And Luke ends up here at some stage. And if we magnified Luke to see exactly what Luke's shirt was, what would Luke's shirt say? He's our superhero. He's our substantial or material derivative. And so we know that the forces acting on bodies, which is really what Bernoulli is equal to mass times acceleration. And this is the acceleration in this particular reference frame, that the reference frame has to be attached to this pencil as it's going down, so it's fixed to it. And so we know that if we look at this, we've done it already, then this substantial derivative, all we need to do is, if we're just working in x and in z and time, we can write this as rate of change of velocity with time that's attached to Luke is equal to rate of change of velocity with time in a fixed coordinate system plus rate of change of velocity with time, and we can multiply it by 1. We did this already once. So dz over dz is just 1. Change in velocity with time, we're adding the components with time. If we're looking at components with respect to x, y, and z, they're all orthogonal to each other. So they have no component in the direction of the other one. So we can write dv dt, we can write dv dt 3 times extra, one with respect to x and y, and they'd all not be additive to each other. And we can look then at what this individual component is. And so we did it last time. So we took this velocity v, which is equal to 2gz. If we translate that to figure out exactly what this term is here in the substantial derivative, it's dv dz times dz dt. Change in height with time is velocity, right? So this is velocity, which means that this becomes velocity times change in velocity with z. If we substitute this into this here, we end up with 2g square root z. The derivative of velocity is z to the half goes to z to the minus half times a half. divided by, multiplied by 2g square root. And so this is this term dv dt. I'm just writing it out. So this term here is no different from this. We're adding those together. So this would be change in velocity with time plus this term here. 2g, square root 2g times 2g is 2g. Z over 2 is this. Z to the half over z to the half, which is this term here. And so that this term is just equal to 2's cancel out. We did this before, right? These cancel out. So equals to 2 dv dt plus g. So the acceleration, which is what dv dt is, change in velocity with time by definition, is just g plus how it changes in time. But this is in a static reference frame. So this is static. And this is following the drop of water. This is following Luke. And so if you think of this here, then what are the individual components? I'm going to try and be fancy and take it out. Doesn't like to do that. Why doesn't it do that? Well, I'm going to do that then, if it doesn't want to do it. So if we look at a static reference frame, then we know from Bernoulli that d phi 2 dt equals 0, right? So if you look at this now and you look at 10 minutes later, the velocity at point 2 is the same. It's not changing. We know that dv dt for the other point also, Bernoulli's steady state, so it's not changing. So relative to this picture that we're taking, points here and here, they're not changing. But we know that dv dt dz dz, which is this term here, is equal to, we've just worked it out, is equal to g. And likewise, at this point, it's equal to g as well. And so the point is that if we want to do the calculation for the forces that are acting that we can use in Newton's second law, F equals ma, this is A, this is attached to the body that's coming through here. And we can define it. This is what I feel if I'm falling down from point 2 to point 3. I go through some acceleration, which is given by gravity. But I could also calculate that if I knew what my velocities were at this point and this point. This point, every time someone goes through point 2, the velocity changing with time is not changing, but the location is changing this. So if I knew, for instance, if I knew what my velocity, change in velocity at 2 with time multiplied by v2, this would also be equal to g. That's essentially what we just did, right? And so it's important to know, to understand things in terms of reference frames, which we'll use. So we'll go back to that as we go through it. So that was really what Monday's class was all about. Did anyone watch Monday's class? Did you see the scores from the question?
On the website for 2021.
Yeah.
We should watch
Yeah. I was going to say that one reason to see 2021, you'll see that the scores from the first test were something like 28%, 30%, 68% for the first test, for the first 3 tests. So based on the averages for your first test, they're worked out quite well. Okay. Yeah, so it doesn't change much. I just say the same thing each year. Not very original, I'm afraid. So that covers the so-called substantial derivative. This is material derivative or substantial derivative. It depends on something, some quantity changing with time. Bernoulli's steady state. So if you take a picture upstream and downstream, those quantities aren't changing, and changing in space, which is this second term. And clearly, it is changing in space vertically. It can be any quantity. This could be mass, it could be velocity, it could be temperature, it could be any kinds of things you could use. Secondly, maybe do this relatively quickly. It's a bit esoteric. So streamline accelerations depend on components that are related to changes in velocity along the streamline, both along the streamline and normal to the streamline. And so if we want to work on accelerations, easy to draw a figure, streamline accelerations like this. This is a radius. This is a streamline velocity. No, let's not do that. This is, well, actually, let's do that. This is a streamline vector. This is a normal vector, n bar. This is velocity along a streamline. And I guess we could write on top of that accelerations in the x direction and accelerations. I think I chose y in this particular case, so let's just choose x and y. And so we know that the velocity occurs along a streamline. Let's see if I can allow me to do this. So I don't write it. See, see if it will take it. I don't know if it'll drag this or not. Oh, no, it's not. Fine. So I'll just write it out. Okay. So we can get from this the acceleration along a streamline is just equal to the velocity times the rate of change of the velocity along the streamline multiplied by this vector s plus v squared over r times a vector n. And so if we want the velocity, the acceleration, this is a vector in x, y, and z. So we need to know what the components of the acceleration are in terms of along a streamline. So this vector along the streamline is always a unit vector, so it's of length 1. So if we look at the components of that in the x and the y, then we could always write this as being 1 and 1, and this then would be 1 squared plus 1 squared is 2 square root. And so this is the vector s. And so we could also divide these through by 1 over square root 2 and 1 over square root 2 and 1 over square root 2. So this indeed is equal to 1. And so these would be the components of the vector in each of the x and y directions. So if we wanted to get the acceleration from the streamline information, so we'd have this information. If this is a streamline, the velocity vs is the only velocity, right? Orthogonal to that, there is no velocity, because it's the principal velocity. Whoops, didn't mean to do that. And so this is a vector. It would be equal to components in the ax, ay, and az directions. And it would be equal to the velocity times the rate of change of velocity along the streamline. So if you know the velocity at this point, you know how it's changing as it goes along here, you know this component. And then this would be just the vector s bar. And the vector x bar is going to be this magnitude here, 1 in x, 1 over square root 2. And the y direction would be positively upwards, and there's no velocity into the page, so that would be equal to this. And the centrifugal acceleration, you remember doing the experiments with imagining spinning something around your head on the end of a string, then that would be equal to the streamline velocity squared divided by the radius through which it's going through, and multiplied through by whatever the normal vector is. So the normal vector, if this is the streamline, then this would be, just to do those same colors, that's not, I didn't want to do that. This is the normal to the streamline vector here, right, in this direction. And so this would be made up of this would be made up of this, and so it would be this. And so if this is 1, just like this is, we can do the 1 over square root 2. This is just 1 over square root 2. It's the same as cosine 45 degrees, right? 0.707. And so this would be x. So this is minus 1. This would be y, which is plus 1. Again, 0. And this would be 1 over square root 2. Just instead of writing these here. And so we've wanted to know the accelerations, should we want to do it, in x, y, and z. We can always get it by transforming from the streamline velocity. There is only velocity along this trajectory. Normal to it, the velocity is 0. So all of these velocities are actually streamline velocities that we'd calculate from Bernoulli. If the radius was infinite, so in other words, if this infinite circle would give a straight trajectory here all the way through, then the centripetal forces would be 0, right? You divide by 0, and you'd only be converting the streamline velocities in a different frame of reference. So that's just a transformation. Not so likely that you'd use that in any way, but it follows on directly from what we've talked about, that this is actually what we call the convective acceleration. And so what that means is that instead of dv dt, if you're attached to this, it means as you go from upstream to downstream. So if you look at the free jet that we had before, we know from continuity that velocity v1 is smaller than velocity v2. And so the velocity is changing as we go along a streamline. And so it's accelerating. Even though the velocity is constant here and the velocity is constant here, a packet of water as it is carried downstream is accelerated by this so-called convective acceleration. It means that it's carried in space. So useful to know. So relates to this. And of course, this term here, v dv ds, is the same as f equals ma. And we've already just discussed that the acceleration we can write relative to Luke, who's falling through the sky, as in this, or we can write it in terms of a static frame of reference, which is what this is in looking at it going downstream. That's really the transformation that we're doing. So a little bit complicated, but maybe it'll make better sense later on. Okay. So that's kind of the first part of today. The more substantive part of today is that now for week 6 and 7 and 8, we'll look at conservation laws. So 6 is conservation of mass. 7 is conservation of momentum. and 8 is conservation of energy. Conservation of mass is you have a 10-liter bucket, you're filling it at 1 liter per second. How long does it take to fill? 10 seconds. That's conservation of mass. If you have an inflow and no outflow, the rate at which it accumulates you can calculate by using this overly complicated expression, but it's useful because we can apply it to these other conservations. If you wanted to write a conservation along a streamline, then actually what we've just talked about is that if fluid flows down a streamline, just as we talked about right now, then if we conserve momentum, mass times velocity along that, then you know that we can write this in terms of Bernoulli as pressure divided by unit weight plus elevation plus v squared over 2g equals constant. And we've said before that if we split this up, this is actually F equals ma. So this v squared over 2g is actually the same as our velocity times dv dx. It's exactly the same, similar term, which is actually equal to a half dx ddx v squared. We can show all of these things. Don't need to worry about it now. But conservation of momentum for a streamline is just looking at the inflow into this streamline, the outflow from this streamline. We know that across these boundaries, the velocity has to be 0, so there is no outflow. So this is a closed control volume. Velocity in times area is volume rate in. Velocity out times area is volume rate out, multiplied by density. It's a mass rate, and it's a momentum. So we'll do that. And also, if we have streamlines which are being put through a system, then if we have a wind turbine being hit by some streamlines, didn't need to make it that strange, you could imagine putting a pump in a pipe and looking at the amount of energy you have to put into a pipe, how much power you have to put into a pipe to make it flow along the length of it, then we might want to look at conservation of energy in the systems. So those are the 3 reasons that we might want to look at those things. And for each of these characteristics, we can use this rather complicated thing called Reynolds Transport Theorem, which looks like this, which looks like kind of complicated, but let's try and explain it in terms of some good physical explanations. So this is the stuff we've done this morning in terms of this. So this is the idea. We can define Reynolds Transport Theorem as in Osborne-Reynolds, as in Reynolds number, which you've perhaps met in passing. And it really is something that can be written for any quantity. So we can choose this quantity to be mass or momentum or energy and substitute it in here. And I think that the quantity B is equal to uppercase B per unit mass. Should check that before I write that. Yes, you see it down here. Whoops. And so this just gives us a formalism of being able to define things. And really what this says is that this is rate in minus rate out plus rate of accumulation of whatever quantity that we choose. It's just, it balances it. So it's easiest to think in terms of mass. So mass rate in minus mass rate out. 10 kilograms a second into a bucket, 10 kilograms a second out of the bucket. there is no accumulation in the bucket, and in equals out. And so this term actually ends up being equal to 0 in the first case that we're looking at. If the rate is 10 kilograms a second in and nothing is flowing out, then the rate of accumulation will be 10 kilograms per second into the container. That's really what it's saying. It's saying it with some integrals and some differentials, but those we can understand in terms of just rates of flow across boundaries. So think of it in terms of that. We can also write this in terms of stationary, moving, or deforming coordinate systems. We won't do, well, actually we will do that perhaps on Friday, but not today. So let's do this just for the case that we're looking at now and talk about what these equations are. This is density for us, well, if we do this for this. So B is equal to mass. Lowercase b is equal to mass per unit mass, which is 1. And so for this ends up being 1 for our case. This ends up being 1 for our case. And we can just concentrate on what these physically mean. And so we'll describe them not in terms of differential calculus or anything. We'll try and define them in terms of physical properties, in terms of what's going. So, well, we've said this. Fine. I'm going to go back. I'm going to start writing stuff down so that we can talk about it and explain it. So I'm going to write Reynolds transport theorem down. Apparently I can't copy it, so maybe I'll make it small so I can actually get it right. I'm just going to write this down. So we're starting a new term. You can get conservation of mass. So d uppercase B dt, substantial derivative, is equal to rate of change with time, integral over the control volume, CV, density, I'll write in B, even though we set it equal to 1, times dV, plus integral over the control surface is what CS is, rho times B times V dot N, dot product, times dA. So I'll make it big. So bad writing when you... So let's see what we talked about from before, and let's see how it makes sense. So we'll choose that for conservation of mass, the extensive quantity, I guess it's called, is equal to mass. The intensive quantity is the extensive quantity per unit mass, which is equal to mass over mass, which is 1. This is the total amount of mass in the big system. The big system isn't changing, and so for our intents and purposes, this whole term is equal to 0. We've said that lowercase b in both cases is equal to 0, is equal to 1 rather. And so what this term ends up being is that 0 is equal to a rate of change of something with time across a control volume, in a control volume, times the density times the change of that volume, plus an integral over control surface times density, times a velocity dot product over an area. And so it's probably easiest to think of this in terms of just a, could be a, let's have a streamline that we've got. And this blue contour is our control surface. This volume here is our control volume. This, if you like. And I guess this is dA, area. And so we know, for instance, that if we have a surface, say we have a control surface, and we have fluid going across that at some velocity. This is a velocity now. What we'd like to do is be able to calculate a unique value for that velocity normal to that boundary. And so the only way we can do that is there's a velocity here. Of course, there are velocities, components to that velocity relative to that. We'd like to know what the velocity is that's normal to that boundary. And the velocity normal to that boundary is just equal to the dot product. It would be this velocity times the cosine of this angle here. And so if you think about a dot product, it's just the component of this velocity that's flowing across this control surface that is normal to the boundary, because that gives us a unique value of that flow rate. And so if we looked at flow rates across this, so let's say we have V1 here, we have V2 here. You could think of this as a stream tube, so there's no flow going across this boundary. And so this would be this boundary would be of some length dA1, or actually A1, let's call it A1, not dA1. Whoops. This area is A1. This area is A2, A3, etc., or A4 rather. Obviously they are lengths, but they have lengths into the pages. And so let's write this equation out. It says that 0 is equal, let's write this a little bit differently. Let's write this as rate of change with time of density times volume. I've just taken this thing out here and put it in here. Plus density times the velocity that's normal to this surface multiplied by its area, right? So the velocity normal to that surface is V1. The dot product when it's an outward normal and the flow is out is positive. You can ask me what plus VE is again. If the velocity was flowing in this direction, the dot product would be negative, right? So the idea is that, let me draw it out actually, probably. So the normal, outward normal to this boundary is this. This is our n hat. This is this. If the velocity is in the opposite direction to it, if it's 1-to-1, cosine theta is equal to plus 1. If it's in the opposite direction, cosine 180 is minus 1. And so this is going into it, so this would be a negative sign. And it would be multiplied by A1. What other ones do we have? We have V3. We could do it for V3, but we know that V3 is 0, so that's 0. We know that V4, the velocity normal to the boundary is 0, so this is 0. We don't have to worry about those. And we know that velocity 2 is the density, these will be multiplied by densities as well, of course. Velocity 2 times A2. If we draw the outward unit normal, it's in the same direction as V2, and so this would be positive. And so this, if we account for this, this merely says that this is equal to rate of change with time of the product of density and the volume minus density times V1 A1 plus density V2 A2. And so we haven't said it, but if the A1 and A2 are the same, then we know by definition that V1 and V2 have to be the same, right? Velocity. And so there can be net accumulation. So we can write out what those terms are in terms of what we just said. And this is accumulation rate plus mass rate in. I guess it's mass rate out minus mass rate in. From our sign convention, right? If it's in, it goes across this boundary, so this is negative. So this is mass rate out minus mass rate out. Has to equal 0. So that's this very complicated expression, and physically what it means, it means that if you have stuff going into the bucket, stuff going out of the bucket, then if it goes in at the same rate it comes out, then it doesn't accumulate. If we want to take it the next step, and maybe I want to add a page. So we just keep on doing this. So the other thing that we can do with that expression, everyone okay with this, I guess I should ask? It's quite an important concept. If we write this out, we could also write this out as 0 equals, let's differentiate this in parts. Rate of change with time of density times the volume plus density times rate of change of volume plus density, velocity times area. That's this expression, this, what we've boiled, yes? Yeah.
Okay. Is for the accumulation rate plus mass rate out minus mass rate in, or is it mass rate in minus mass rate out?
So in this, well, you have the sign convention is, I'm not sure exactly how to write it, but if it's mass is going in, it's a negative sign in this relationship. If mass is coming out, it's positive, because this outward normal to the boundary is aligned in the direction of the velocity. So this is a positive velocity. So this is positive here, and this is negative. And the reason, yeah, I guess that's a bit complicated, right? So you know that we work in terms of, yeah, this is worthwhile doing. So we work in terms of x and y. So by definition, V1, forget what I said here. This is V1. This is positive by definition. Okay? But the product, V1 dot n, is negative, because this is positive and this is in the opposite direction. Very important concept. You can do it by working out the dot products, and they'll give you that. And really it is because this is the velocity times cosine theta. Theta is equal to 0. Theta is just the angle between them. So the product of them is 1, positive. If theta is equal to 180 degrees, then cosine 180 is minus 1, which is what this dot product is multiplied by. So it comes out to be negative, right? So it's basically saying the component of this velocity in this direction is minus v1. So, okay. And so this is the basic expression that you'll have to use. You can think of it in these terms rather than this integral. And you can think of two examples, I suppose. They're written out. Take the tire example. Ignore the fact that a tire gets a bit bigger when you pump air in. So if we wrote this expression for this, this would give us take note of the V's with bars through them and the V's not. Velocities versus volumes. So if we wrote this conservation equation for this, what would that give us? We have the volume of the tire multiplied by the rate of change with time of the density of the fluid we're pumping in it. You know that the pressure goes up when you inflate a tire. You know from the ideal gas law that pressures and densities are linked, right? Don't need to write that out. Plus density times rate of change of volume with time. Imagine it's a steel-belted radial. Volume doesn't change with time because it's very rigid. So the volume changing with time is 0. And the sum of density times velocity 1 times area 1 is finite. So the density is the air going in. It's going in at some velocity over the area of the valve. So this is a rate in. So in this case, V1 dot n, this is V1. The unit normal is outward, so V dot n would equal to minus V1. So this would be minus. Everything else is positive. Density is positive, area is positive. This is, so in other words, the expression would be that volume of the tire times the change in density with time, just by taking this onto the left-hand side, would equal to density times velocity 1 times A1. We'd integrate this with respect to time, multiply both sides by dt. So if we define this behavior as the integral between 0 and 1 of density as it's coming in times the area times the velocity, and we integrate with respect to time, that's just t1 minus t0, which is the duration, and that is equal to the volume multiplied by the integral from 0 to 1 of the density, which is equal to the volume times density 1 minus density 0, if you do it in the same units. And so the units of this are going to be density kilograms meters cubed times meters squared meters per second time. I guess that time is seconds, of course. So this is meters cubed per second times kilograms, and this is equal to volume, which is meters cubed kilograms per meter cubed, which is also kilograms. So the units balance out, and just define the amount that is there. So if you want to solve for something in this particular case, if you knew what the initial density was, and you knew what the initial density was, and you knew how long you were pumping gas in, you could calculate exactly for a known volume what the final density would be. And if you know the final density, then you can calculate the mass that's gone in, because you know that mass would be equal to the volume times the final density. Volume's meter cubed, kilograms per meter cubed gives you mass. And so that's all you need. So that's it. Okay?